let's get started with today's class. If you recall, we were discussing relative stability. Please recall that this is the closed loop transfer function of the class of systems that we are considering, right? G of s divided by 1 plus G of s h of s, right? And in the previous class, we discussed what was relative stability. The notion of relative stability has to do with the fact that how robust my system is, as far as the location of its poles are concerned, right? So that is, if I perturb the system, if there is some unmodeled dynamics or like some parametric variations, how do the poles that are closest to the imaginary axis change? And is there a chance that, the poles may reach closer and closer to the imaginary axis and perhaps cross over, right, at some point or the other. So that is a notion that motivates the concept of relative stability. Kindly recall that the presence of all poles in the left of complex plane implies what is called as absolute stability. What we have been calling as stability is absolute stability. Now we are adding an adjective before that, right? We are essentially learning what is called as a relative stability, right? And we figured out in the last class that the closeness of the g of j omega h of j omega locus to the -1 point in the g of s h of s plane is indicator of relative stability, right? So because when does a stable system become unstable? When its poles cross over, right? When they cross over, s is of the form j omega, right? And our closed loop characteristic equation is 1 plus g of s h of s. So when s is of the form j omega, we get 1 plus g of j omega h of j omega equals 0. That means that g of j omega h of j omega equals -1 when the poles cross over. That is why, how close is my plot of g of j omega h of j omega to the -1 point in the g of s h of s plane. That's indicator of relative stability, right? So in that sense, we essentially define two terms, what was called as the gain crossover frequency and the phase crossover frequency. The gain crossover frequency is the frequency at which the open loop transfer functions, open loop sinusoidal transfer function magnitude becomes 1, or in other words, the magnitude of g of j omega g, h of j omega g is equal to 1, right? The phase crossover frequency omega p is the value of omega at which the phase of the open loop transfer sinusoidal transfer function becomes -180 degrees. And why are we worried about 1 and -180? Because that characterizes the -1 point, right, in the complex plane, right? So that's why we are focusing on that point. So let me build on this. Okay, this is where we stopped in the previous class, and we did a numerical example, right, to calculate omega g and omega p. So let's build on this. So suppose, let's say, I draw the g of s h of s plane. Okay. Now, what I do is that, of course, we are looking at the -1 point. Let's say this is my -1 point, right? So, and let's say this is the origin. Okay. So obviously the -1 point has a magnitude of 1 and phase of -180, right? Suppose, let us say, just for the sake of argument, right? Let us say, my locus of g of j omega h of j omega is something like this. Okay, so some open loop transfer function whose locus is this way, right? So now the point is how, or let me redraw it a little bit. No, so sorry about that. So let's say, I just take some. I'm just taking some. Transfer function, okay, which essentially goes like this, right? Open loop transfer function. Now, obviously, the locus doesn't pass over the -1 point, right? So at least to begin with. Now the question is that how can I graphically locate omega g and omega p in this particular plot? This is the Nyquist plot, right, of this particular open loop transfer function. That's what I have drawn, right? So I am just taking some arbitrary curve, right, to just convey the concept. So now how can I locate omega g and omega p in this diagram? So let us say, I draw a circle of unit magnitude, right? So sorry. oops, sorry, I think I erased the whole thing, right. So, let us say, like I have some transfer function, like which essentially goes like this, and let us say, like I am just drawing some arbitrary shape, right. So, let us say, like I draw a circle of unit radius, right, and then figure out where this circle cuts the what to say, the Nyquist plot, right. That is my omega g, the gain crossover frequency. Okay. Now, let us say at omega equals omega g, like I have a phase which is equal to this number, okay, or a negative phase which is equal to this number. Okay. Now, let us say if I at this frequency, let us say I want to make the system tend to instability, what will I do? I would just try to shift this curve such that I keep on rotating it about the origin, so that this particular point which is here should come to the -1 point. How can I do that? If I rotate the entire Nyquist plot, let us say by this angle gamma, right. Do you agree that this point will travel on this red dotted circle of unit radius and then come and settle down at -1? Do you agree? Does everyone agree? Okay. Please remember that point. Similarly, where is omega p? Where it becomes -180. So, in this example it is, let us say this is omega p. Now, let us say I want to make this point come to -1. What should I do? I should just scale the curve, right, by some number. Okay. In this case I am multiplying, in a general sense I should scale the curve, right, so that the phase does not get changed, like I am just moving the magnitudes, I am just changing the magnitude alone, right. So, that is what I need to do, right. So, this leads to two definitions, okay. So, that is what I am going to write down. So, we will refer to the this figure once again. So, the gain margin K subscript, okay. So, let me write down the definition, then we will figure out why it is defined the way it is, okay. It is the reciprocal of the magnitude of the open loop sinusoidal transfer function g of j omega h of j omega at omega equals omega p, right. Why? Because what is this, what is say magnitude from 0 to this point at omega p, that is the magnitude of the open loop transfer function. Now, if I take the reciprocal and scale the entire open loop transfer function by the reciprocal, what will happen to this point? It will pass through the -1 point, right. That is the motivation behind the definition of the gain margin. Is it clear why gain margin is defined like this? So, the gain margin, the expression for the gain margin K subscript g is going to be 1 divided by g of j omega p h of j omega p, okay. That is how we write it, okay. So, in other words, this is also indicated as -20 log of the magnitude of g of j omega p h of j omega p in decibels. Okay, in decibel units this is the expression. Okay, so you can write it in the absolute units or the decibel units. Is it clear how we define gain margin? So, why am I defining gain margin like this? Because you see that if I draw a vector from the origin to the point omega p, the length of this vector, okay. So, if I take this length, so let us say like I take this length, that is going to be the magnitude of g of j omega p h of j omega p. Now, let us say I calculate a number which is the reciprocal of this number and I multiply the entire open loop transfer function with that number. What is going to happen? This entire curve is going to be scaled and this point at omega p will now go to minus 1. That means that the system is being pushed to the verge of instability, right. That is why it is called gain margin, right. How much margin do I have before the system can become unstable. And why is it called gain margin? Because see, sometimes the scalar parameters which come in the transfer function, right, can have some uncertainty, right. So then the question is that how much tolerance can I have before I push it. And even the poles and zeros also affect the gain, the steady state gain of the system, as we already seen, right. So then the question becomes, like how would their locations also influence the changes in the gain of the system, right. So that is what we are essentially interested in, okay. So that is the definition of the gain margin. Is it clear? Yeah.
Gain margin is defined at omega equal to omega
p. Yes, exactly, yeah. So it's a reverse arrangement, right. So the gain crossover frequency is not used to define the gain margin. The phase crossover frequency is used to define the gain margin. We will shortly see that the gain crossover frequency is going to be used to define the phase margin. Okay, so the next parameter which we are going to discuss is what is called as the phase margin gamma, okay, which I have just indicated there. Okay, the phase margin gamma So, what is a phase margin? A phase margin is the additional amount of phase lag that needs to be added to the phase of the system at omega equals omega g to bring the system to the verge of instability. Okay, that is the phase margin. Okay, so as we discussed, this is omega g, right. So the magnitude of the open loop transfer function at omega g is 1. Suppose imagine that you rotate the entire Nyquist plot by this angle gamma, right. So then what is going to happen? This point is going to come to the minus 1 point. So once again we are going to have the system being pushed to the verge of instability, right. So that is the phase margin. So how do we calculate this? The expression for gamma is this way. So essentially what we do is that we calculate the phase of the open loop transfer function at the gain crossover frequency. Please remember that, okay, and subtract it from minus of 180, right, because typically we deal with proper transfer functions. So the phase of the transfer function is going to be by and large, so essentially when we deal with strictly open loop transfer functions, the phase of the open loop transfer function by and large, okay, is going to be negative. It can be positive in some instances, we'll see, okay, when we want to add phase to the system, but by and large I am saying, okay. So the first number is going to be by and large negative. So then you subtract it from minus 180, okay. So the equation for this is going to be 180 degrees plus the phase of the open loop transfer function at the gain crossover frequency, okay. This is the formula for calculating the phase margin of the system. Is it clear? Okay. So that is the expression for the phase margin. Yeah. Gain margin, yeah. Yeah, it's just that what to say, that is essentially what you need to do is that at the phase crossover frequency you want to push the curve so that it goes and sits at the -1 point, right. So, the question is that how much should you scale it by? You should scale it by the reciprocal of the magnitude at that particular frequency, right, the phase crossover frequency. This is what, here you are rotating, that scaling, here you are essentially rotating the thing, right. So, yeah, okay. So, that is what we are doing. Is it clear? Okay. Now, typically, now this is a node, okay. So, okay, for given a system whose open loop transfer function does not have poles, zeros in RHP, okay, both the gain margin in decibel units, right, and the phase margin in degrees should be positive. To ensure the stability of the closed loop system. Okay, this is a result. Okay, so I am just conveying this to you, right. So, yeah. So, one may typically wonder, like why we not want the gain margin and the phase margin to be positive. This is the result, right. So, that is if you want to ensure closed loop stability for a certain class of systems, like which do not have poles, open loop poles and open loop zeros in the RHP, right. You essentially make sure that the gain margin and the phase margin, the gain margin in decibel, okay, and phase margin in degrees need to be positive, because gain margin can also be less than 1, okay. It should be a positive scalar, right, because you can have, it is a reciprocal of the magnitude of the open loop sinusoidal transfer function at omega p. Suppose let us say the magnitude of g of j omega p, h of j omega p is 10, what will happen to the reciprocal? It will become 0.1, right. So, then we need to be careful, right. So, that is like we can just have what to say take the absolute units. So, essentially that is why we take the gain margin in decibel units to be positive. Okay. Now, the another interpretation of the gain margin and the phase margin using the Bode diagram is this following. Okay. So, let us say I draw the Bode diagram of the open loop transfer function, right. So, the magnitude plot and the phase plot. So, let us say I am drawing the Bode plot of the open loop transfer function. Okay. So, let us say this is the 0 decibel value, okay, for the Bode plot, and let us say this horizontal line represents -180. Okay. So, now if I draw the Bode plot, okay, the magnitude plot and the what to say phase plot in this manner, where do you think is the gain crossover frequency and the phase crossover frequency? Let us say this is the Bode plot of the open loop transfer function, right. So, where is the gain crossover frequency? See, because we interpreted gain crossover frequency, phase crossover frequency, gain margin and phase margin in the Nyquist plot. Let us do the same thing in the Bode plot. Suppose let us say I give you the Bode plot, you should be able to figure these things out, right. So, what is the definition of the gain crossover frequency? It is the frequency at which the magnitude of the open loop transfer function becomes 1 or 0 decibels. So, where do you think the gain crossover frequency will be? Yeah. So, wherever the curve cuts the 0 decibel line. In this case, since I have taken this value as the 0 decibel, so to essentially graphically be consistent. So that's what that's where omega g will be. Now what about omega p? Place where the phase becomes minus 180 degrees. Where will it become minus 180? Here. Okay. Now how can we get the gain margin and the phase margin? Now if I extrapolate this, right, this is going to be what? The phase of the open loop transfer function and the gain margin, right. So then what will be the at the gain crossover frequency. Now what will be the phase margin? From this angle you need to subtract minus 180. What does it mean? That means that this is the phase margin. So this is a positive phase margin. Okay, so if you get a Bode plot like this is the phase margin, because like you are getting the difference between the phase at which the gain crossover frequency and minus 180. Since the gain crossover frequency phase is less negative than minus 180, you are going to have a positive phase margin. Now how will I get the gain margin? At the phase crossover frequency, I go to the gain plot, right, the magnitude plot. Now what is this? This is the magnitude of the open loop transfer function at the phase crossover frequency. So the gain margin is going to be the reciprocal of that, or in decibel units it is going to be the negative of that, right. So this is going to be the gain margin. Is this going to be a positive gain margin or a negative gain margin? It's going to be positive, right, because this number is negative. So you want to take the negative of the negative number, right? Do you agree? Yes. So this is going to be a positive gain margin. Okay, if it were the other way around, right, it would be a negative gain margin, right, because of the phase crossover frequency, the magnitude of the open loop sinusoidal transfer function is negative in terms of decibels. In this example, I just drew some arbitrary curve, right. So you need to take the negative of that number, right, so which happens to be positive. So you have a positive gain margin if the magnitude in the magnitude plot, the magnitude of the open loop transfer function, the phase crossover frequency is below the 0 decibel line. That's a positive gain margin, right. You have a positive phase margin if in the phase plot, the phase of the open loop sinusoidal transfer function at the gain crossover frequency is above the minus 180 line, right. It's negative otherwise, right. So that's how we interpret gain margin and phase margin. Is it clear? Okay. Now let's go back to the example that we did, right. So this is what we considered, right. So consequently the sinusoidal open loop transfer function is going to be equal to 1 divided by j omega times j omega plus 1, right. Now if you recall, what were omega g and omega p? We had already calculated, right. Recall that omega g was, what was the value of omega g? Correct? Yes or no? I think we did this example in the previous class, right? That's where we stopped, right. So if I recall, let me go back. Yeah, I think this is where we stopped, right. We did this example, we calculated omega g as 0.7862 radians per second, omega p was infinity, right. Okay. Now what does this imply? Gamma, the gain margin gamma is going to be equal to 180 degrees plus the phase of the open loop transfer function at the gain crossover frequency, right, which is this. So, what is the phase of g of j omega, h of j omega, the gain crossover frequency? See, in general, the phase of the open loop sinusoidal transfer function is going to be, from this result, it is going to be minus 90 minus tan inverse omega, right, by looking at this function, right. So, you just plug in omega equals omega g. So, you are going to get tan inverse of 0.7862, right. So, can you calculate and tell me what you get? So, you will get around 51.83 degrees, right. So, that is the gain margin, sorry, phase margin, okay, for this particular transfer function. So, what about the gain margin? See, gain margin is the negative of the gain of the open loop transfer function at omega equals omega p if you go look at the measure in decibels. Now, as frequency tends to infinity, what do you think will happen to the magnitude plot of this particular transfer function? What are the values of n and m? N is 2, m is 0. So, what is the slope of the transfer function? So, sorry, magnitude plot? Minus 20 times n minus m, which is going to be minus 40 decibels per decade. So, you have a magnitude plot which is going to go like minus 40 decibels per decade at high frequency. So, at omega, as omega tends to infinity, what will be the magnitude of the magnitude, what is the value of the magnitude of this sinusoidal transfer function in decibels? It will tend to minus infinity, right? Do you agree? So, then gain margin is in decibel measure, it is a negative of that, right. So, then what will happen? It is going to be correct. So, you can also look at it this way, right. So, the magnitude of the open loop transfer function is going to be essentially 1 divided by omega times omega square plus 1, right. This also will give the, right. So, essentially we see that it has infinite gain margin in the sense that like it is very tolerant to disturbances in the gain, okay. So, that is what happens with this particular factor, right. You need to really essentially push the gain to, that is you need to scale it up by infinity to even make the system to the verge of instability at the phase crossover frequency, okay. So, that is going to be what to say, not essentially feasible, right, practically. So, that is the point here, okay, because the phase never reaches what to say minus 180 only asymptotically, that is the point here, right, okay. So, that is the calculation of the gain margin and the phase margin, is it clear?